I apologize for that, guys. My computer completely froze, and I'm hoping that I saved the right version of this PowerPoint because it completely froze in the midst of that. So we're going to try this again and see how we do. It was just completely frozen. Okay, so one thing I do want to tell you, all of these models are useful for certain things. Remember that models are exactly that. They are our way of trying to describe what's happening for something that we can't see. So all of these models are used to explain certain aspects of the way the molecules, with the way they are shaped and how they react, excuse me, and things like that. One thing that you should be aware is that there are exceptions to VSEPR. Remember, valence shell electron pair repulsion is a theory that just says electrons are going to want to get as far apart as possible because they're like charged. And we explain how they do that and how they adopt those shapes using hybridization or valence bond theories. One thing you should note is that as the central atom gets bigger, those electron domains don't impede each other as much. And so we can look at these molecules. These are all in the same group, H2O, H2SE, and H2TE. All of those central atoms are members of the same group, but each one is one period further down and therefore bigger. And look at what happens to the bond angle. When you get to tellurium up here, you're essentially not having to adopt hybridization or the theory of hybridization at all. It's perfectly comfortable bonding those two hydrogens 90 degrees apart because those electron domains are far enough apart in space. So that's one of the reasons why I like to say we don't necessarily say that the bond angle, when we see a molecule that's shaped like this, we don't necessarily say that it's 104.5. We say that it's less than 109.5, because once you incorporate other atoms in there, the difference, there's going to be a difference in the size of that bond angle. Okay, so this is the last part of the chapter, and I'm going to go through this fairly quickly. I will tell you when I'm done what you need to know of this. This is a new theory. Remember at the beginning of this chapter, we said we had a couple of problems. One of them was geometry. We couldn't identify how those shapes that we would predict from VSEPR would arise using atomic orbitals. So we had to come up with a way to do that. The other problem we had was magnetic properties of atoms. And we particularly talked about oxygen. When you have unpaired electrons, those unpaired electrons will generate a magnetic character to an atom or a molecule. And we can see that if we use a Gouy balance, and let me talk a little bit about the way this Gouy balance works. If you measure the mass of a sample, we have a sample in here, and we measure it. In the first place, you would measure it without exposing it to these electromagnets and get a mass, balance its mass. But then if you turn on these electromagnets, if this sample is magnetic, the action of the magnets would be to drag that sample down, to hold it back and not allow it to be measured in the same way. And it will appear to be heavier. So when we do that with oxygen, liquid oxygen, we actually see that oxygen has a magnetic property. That would indicate that it has unpaired electrons. If we look at its Lewis dot structure over here, though, we see that there are no unpaired electrons. So we can't explain this with any of the theories that we've done thus far. So we have a new theory called molecular orbital theory. And if you remember, we talked about linear combination of atomic orbitals before when we talked about hybridization. What we were talking about there was within one atom, orbitals within that atom hybridizing or combining through this linear combination to form new orbitals for that atom for the purposes of bonding. What we're talking about in molecular orbital theory is atomic orbitals on neighboring atoms combining through linear combination of atomic orbitals to yield orbitals that are delocalized, not isolated on a particular atom, but delocalized over the entire molecule. It's still a mathematical process of combining wave functions. If they are in phase, if the waves are in phase, they will add together and form a larger wave. If they are out of phase, they end up canceling each other out. In other words, we're going to create two new orbitals. One is in phase, it's called a bonding orbital, and the other is out of phase, it's called an anti-bonding orbital. So let's see what that looks like when we start combining orbitals. These represent two s orbitals on two neighboring atoms. When they come together, they combine. If you add them together, they form a stronger orbital that is delocalized over the entire molecule. Much of that, it's kind of a football-shaped structure. Much of that region lies between the two nuclei. Therefore, it is a sigma bond, and it's a bonding orbital. We call this a sigma s orbital because it is formed from s atomic orbitals. If we subtract those, remember we can add or subtract. If we subtract them, we create regions in space where most of the region for electron density is outside the two nuclei. Thus, these two nuclei are sort of repelling each other. We call that an anti-bonding orbital, and we give that the designation sigma star s. Sigma, because it lies on the axis of the two nuclei. Star, because its electron density region is outside the nuclei, so it acts to destabilize the molecule. And the S means that it comes from the s orbital. If we're combining p orbitals, we have one p orbital, the one that's on the x-axis, that can approach end to end. That's going to form a sigma orbital. The bonding molecular orbital creates this large football shape between the two nuclei. The anti-bonding has most of the electron density outside the nuclei. It's the same principle with hybridization in the atomic orbitals. If you add two orbitals together, you have to get two orbitals out. The same thing is true here. Don't get thrown by the fact that we're calling one of these an anti-bonding orbital. It just is referring to the region in space where most of the electron density lies. Now, as I said, only one p orbital can overlap end to end. The other two, the one on the y-axis and on the z-axis, will form side to side. They are above and below. So they are going to form slightly different shapes. They're going to form this region above the plane of the nuclei and below the plane of the nuclei. This is the bonding orbital. We call that a pi p orbital because it's above and below. That's why it's a pi orbital, and it's formed from a p atomic orbitals. And then the one above is called the pi star. That's the anti-bonding orbital. So I'm going to walk you through the molecular orbital energy diagram. Don't worry, you're not going to have to do this. I'm going to give you a chance to practice one, but you're not going to have to do that. They can be very simple or very complex. You can draw one for uh, two hydrogen atoms coming together. It's just through the 1s. It's very simple. But we're going to look at the one here that's for fluorine. What we have on this side, this is one fluorine atom, and in green you see the electron configuration of that fluorine atom. On the other side, you see a second fluorine atom in the molecule, and these in green you see its electron configuration. 2s, we skip the 1s because the 1s, by the way, looks very similar to this. It's just lower energy. But we combine these two 2s orbitals. We're going to create two molecular orbitals. The sigma 2s is lower in energy. It's a bonding orbital. The sigma star 2s is higher in energy. It's a destabilizing orbital. Nonetheless, it has to be filled with electrons. So these 4 electrons will populate the sigma 2s and the sigma star 2s. When we look at fluorine, when we look at the 2p's up here, we have 5 electrons on either side. We have 2 choices for our bonding orbitals and 2 choices for our anti-bonding orbitals. We have a sigma 2p and we have the 2 pi 2p orbitals. And we have 2 pi star 2p's and we have 1 sigma star 2p. So our 10 electrons will go lowest energy first. We follow the same off-ball principle we did for atomic orbitals, filling lowest energy first, 2 electrons with opposite spin, and we start with the sigma 2p, the 2 pi 2p's, the 2 pi star 2p's. And that's the electron configuration or the molecular orbital energy diagram for a fluorine molecule. Now, this allows us to have a new way of determining bond order between 2 atoms. And the interesting thing about this particular model is that you can end up with bond orders of 1.5 or 2.5 or 1/2. And you do that because the bond order is you take the number of electrons in the bonding orbital, molecular orbitals, subtract that from the number of number of electrons in the anti-bonding molecular orbitals and divide the answer by 2. So we have 2, 4, 6, 8 electrons in bonding orbitals, and we have 2, 4, 6 in anti-bonding molecular orbitals. So 8 minus 6 is 2, divided by 2 is 1. The bond order in fluorine is 1. If we had an odd number of electrons in this anti-bonding orbital, you would end up with a bond order of 1/2. So that's how you end up with fractional bond orders. So when we look at the molecular orbital energy diagram for oxygen, here are our 4 electrons in the 2p, and we populate them 2, 4, 6. And because these pi star molecular orbitals are degenerate, just like our p orbitals were degenerate, we populate them one at a time with electrons with parallel spins. And that's why we have a magnetic property. These are our unpaired electrons in the pi star molecular orbital. When we look at the bond order of this, we take 2, 4, 6, 8 electrons in bonding orbitals and subtract from that 2, 4 electrons. 8 minus 4 divided by 2 gives you a bond order of 2. So we still get the same bond order. It's a double bond, but now in this case, we have these unpaired electrons, which give us the magnetic properties of oxygen. All right, so this is very quickly through a completely new model. And the diagrams look very complex, and what the heck is she talking about when she talks about anti-bonding orbitals? we're not going to spend a lot of time with this model. What you do need to know about it is that you really can't predict the molecular orbital diagram. They can be pretty complex, especially in multi-atomic structures. You can determine the number of valence electrons that are going into the diagram. You can fill the diagram with valence electrons starting using the Aufbau principle, starting from the lowest energy first. So let's look at this, and you can determine the number of unpaired electrons. So let's do this for nitrogen together here. I've shown you the ones before, but nitrogen is going to have 2 electrons in the 2s, and it's going to have 3 electrons in the 2p. So remember, on the side here, what I'm showing is this is my nitrogen 1, and this is nitrogen 2, and in the center, this is our nitrogen molecule. So we're going to populate from the lowest energy first. We have 4 electrons to distribute, which we've done. Now we have 6 electrons to distribute, so we're going to do 1, 2, those are degenerate, so I do them one at a time, 2, 3, 4, and then 5 and 6. And I've used up all my electrons. So that would be the molecular orbital diagram for nitrogen. Bond order would be 2, 4, 6, 8 electrons in bonding molecular orbitals minus 2 in anti-bonding orbitals equals 6 divided by 2, 2 disappeared, is equal to 3. So we have a bond order of 3. The bond order should always agree with what our Lewis diagram shows us, and in fact it does. So that is the molecular orbital theory. Let's take a look at a comparison of the two. Valence bond theory considers bonds as localized between one pair of atoms. All of the electrons you see are either they're lone pairs centered on one atom, or they're localized between one pair of atoms. Molecular orbital theory considers electrons delocalized throughout the entire molecule. The valence bond theory creates bonds from an overlap of atomic orbitals, either sp and d orbitals, or hybrid orbitals, sp2, or sp3. So that's creating the overlap. For molecular orbital theory, you're combining atomic orbitals to form molecular orbitals, and that's where the electrons are residing. So not in an overlap of orbitals, but in a molecular orbital. We get sigma and pi bonds in valence bond theory based on where those bonds, where that bond occurs, whether it's on the axis between the two nuclei or outside of that axis. Molecular orbital theory creates bonding and anti-bonding orbitals based on interactions on which orbitals are filled. This valence bond theory would predict the shape based on the number of regions of electron density in the atom. We can't predict shape using using molecular orbital theory. Molecular orbital theory doesn't tell us anything at all about shape. It only predicts the arrangement of the electrons in the molecule. One of the failings of valence bond theory and Lewis dot structure is that we sometimes need multiple structures to describe one molecule, because we have an extra pair of electrons we have to show, and it could be between one pair of electrons or a different pair of electrons. It can move throughout the molecule in the different resonance structures. And so that highlights one failing of valence bond theory. The fact that we have to invoke resonance suggests that there's a flaw there. Resonance structures don't exist in molecular orbital theory because the electrons are already dispersed over the entire molecule. So one of the things that we end up doing with this is we combine both theories and think of the sigma bonds as being localized bonds, and those double and triple bonds, that pi bonding, we can think of as being localized or delocalized throughout the entire molecule. And you'll see structures where they show delocalization over like a carbonate ion. Instead of having 3 different resonance structures, you would show that extra pair of electrons as resonating over the entire molecule. So that basically is chapter 5. That is the last of the material that is going to be on the exam next Thursday. As I said, I will entertain questions now. I'll entertain questions next Tuesday. We are going to start chapter 6 next Tuesday, but I will entertain questions as you're studying. Once I meet with my colleagues tomorrow, I will try to send out a message that will at least list the major topics that will be on the test. And I'll certainly be able to give you more information next Tuesday. So, any questions?
Can you hear me?
It sounded like somebody had a question, or maybe there was just talking in the background. I don't know, but.
All right. How much of 5.3 is going to be on the test?
The molecular orbital theory? Yeah. Not much. As I said, molecular orbital theory becomes much more important when you get into organic chemistry and higher levels of chemistry. What I want you to know is probably 3 main things. 1, you cannot predict shape with molecular orbital theory. You need valence bond theory to do that. Number 2, it does address the magnetic properties of molecules that valence bond theory does not. So it does explain something that needs explaining that the other theory cannot. And it also, we tend to use kind of a combination of the two to describe molecules whenever you have to invoke resonance. Whenever you have to use resonance to explain a structure in valence bond theory, understand that we usually treat the single bonds as localized bonds, and that the resonance is a delocalization of electron density that can be explained through molecular orbital theory. But outside of those 3 things, really, you won't have to use it at all.
When drawing resonance structures, do we draw the, I know you can draw the 2 of them or 3 of them with the lines, or you can just write the single bond and then the dashed bond.
The dash line. The dash line is what we use. That's where you're incorporating molecular orbital theory. For our purposes, I would prefer you to draw the resonance structures with single and double bonds and not try to use the dashed lines. But those dashed lines are our way of representing that delocalization of electrons, which is explained through molecular orbital theory. It's a little hard. It's a little hard to show one pair of electrons shared between, like in a carbonate, between all 4 atoms, and so it's better to draw the resonance structures, but understand that that extra pair of electrons is probably really delocalized.
Okay, thank you.
Okay. It's also easy to recognize it as delocalized when you recognize it is pi bonding, so it's above and below the plane that the atoms occupy, and so you can see that would be more delocalized. So somebody else.
Professor,
Yes,
for resonance structures, can you have a triple bond and a single bond?
yes,
Okay,
yes.
but that would be less stable though.
It depends. It depends upon, I think you did one NCO that could have two double bonds or a double bond, excuse me, a triple bond and a single bond. It depends on formal charge. Sometimes, I think you did one in your lab that was N2O. And I think you had two possibilities for the skeleton. One was NNO and the other was NON. And when you do the possible resonance structures for each of those, you find that NNO is more stable. And it turns out that a triple bond and a single bond, based on formal charge, is more stable in that structure. So it really depends upon the atoms involved. Sometimes that will be more reactive, sometimes not.
Okay, thank you.
Yep. Any other questions? I don't know if you can hear him. My dog is snoring. He's snoring to beat the band over here. He would wake the dead. Anyway, if you have any questions, by all means, shoot me an email. We can set up a Zoom meeting. I will know more after tomorrow, after I've worked with my colleagues to develop our test bank. And I will try to give you, this seems like a lot of material, but the most of the material was in chapter 4. Chapter 5 is fairly short. That last part of chapter 5 is really not going to be part of it. It's mostly valence bond theory and hybridization. So most of it, there's a lot. Oh, and I will tell you this, I am not going to test on naming. I am probably going to give you an opportunity to do a quiz on naming. And that quiz will be a video quiz using a site where you have to name or write formulas or give names. And I will give you multiple tries at it to score 10 out of 10. And you can submit it via video. I'll let you know about that, but that will not be part of the exam. That will be separate. Some teachers have not done naming now. They're doing naming later, even though it's in chapter 3. They're doing it later. I think they felt, I guess it was in chapter 4. I think they felt that it was just too much all at once.
You mean naming the ionic compounds and then the acids?
Yes.
Stuff? Okay.
Yes, that will be done in a video quiz separate from the exam.
Okay.
And when I do that, I actually, there's a website that you can use where you can put settings in for, if you want to just name ionic compounds, if you want to name using polyatomic ions, if you want to include naming acids, you can set parameters. I will tell you what parameters you have to use on that, but you will actually be using that website and you'll get your answer right away, how many you got right. And when you get 10 out of 10, submit it. You have lots of tries on that one. So I'll let you know. I'll post that sometime probably after the exam next Thursday. Okay, any other questions?
Wait, can you just clarify what chapters are going to be on the exam?
3, 4, and 5.
Alrighty, thank you.
No, not so much 5.3, but 3, 4, and 5. Okay.
Is chapter 3 is about the speed of light and then
Yes, I know.
frequency and
Doesn't
stuff?
it seem like that was an eon ago that we did that?
Yeah, I look at notes, I'm like,
And
what?
and electron configuration, yes, it seems like it was just that. It seems like a year ago we did that, but yes, that's chapter 3. Chapter 4 is naming and Lewis dot structures and all of that. So yeah, chapter 4 was the big one. Chapter 4 was a tough one. And as I said, naming will not be part of it. So you can skip that part when you're studying. And eventually you're going to have to do it, but not for this exam. Okay, we done? Okay, everybody.
Thank you, Professor.
You're welcome.
Thank you.
Have a nice day.
Have a nice day. Have a nice weekend.
You too.